recording. All right, so yeah, we're gonna start by talking about data sets. So a couple of links I want to introduce. The first one is called UCI Machine Learning Repository. So you can just put these words in a Google search box, you type it in, and it will bring you here. So you just click on the link and it will bring you to this website. So what this means is it's kind of like a database that has all public data, and you can just click in here and you're gonna see a couple of things. The first thing is obviously you have a set of new data that's just uploaded, or you have sets of famous data that pretty much everyone knows. So if you've gone through a machine learning course, undergraduate school, which I'm assuming most of you guys will do that, then chances are you're gonna see a bunch of these data, and these are actually very famous data. So when I say famous data or popular data, I meant the data that easily download. There isn't a whole lot of data processing. You pretty much just download data, and you know exactly what's your X, you know exactly what's your Y, and you just build a model, right? So hopefully that's clear. And if that's not clear, then chances are this data may take you some extra time to babysit. Okay, so that's what a clean data mean, or that's what a popular data set mean. Okay, so at least on this website. So let's go through it. How would you get started, right? First of all, you see this, view all data sets. So that's actually a link. So click on that, and it will bring you to here. This is actually a big table of the link of a bunch of different data sets. Now, of course, you can filter through different thresholds or different, attributes or different features on the left-hand side. So maybe you feel like, hey, I'm just going to do classification, then click on the first link. Or you say, hey, I'm only going to do regression problem, then click on the second link, and so on and so forth. I don't particularly care what you guys do, as long as you guys like it and you guys find it interesting. So that part, I'll leave to you guys. In this field, I can teach you pretty much everything, right? The only thing I can teach you guys is passion. If you're not interested in data set in the beginning, there's very little that we can do, okay? So that part, I rely on you guys. So, I rely on everyone here to help me out to, get the project started. So exactly what task is this? What is it that you're trying to predict? What kind of data set is it? What field is it? That's completely up to you and your teammates. Okay, I'm completely indifferent. Okay, it's not that I don't care. It's because if I care too much, then it shifts direction. Then this starts to become a lecture and start to become like a homework, and you start to stamp on it. And when you stamp on it, that's not how you learn data science. One thing I would want to mention is in regards to this big universe that you can do whatever you want, right? There are a few premises that you want to be aware of. The first one is called number of attributes. Okay, the second one is called a number of instances. The number of attributes is referring to the columns in the data set, right? You download it, you load up to Python, you have a data frame, it's the columns. So think about it. If the number of attributes is less than 10, what's the point of doing neural network? Right? There's 0 point doing neural network, right? So you can just do a linear regression, or you can do a logistic regression, or whatever, right? Build a decision tree, right? You get away with it. Okay, so that's one thing I want to mention. If you want to build a neural network, then you probably should not click on that box, right? Because that means your data sets are all going to be limited within 10 columns. All right, so that's one thing. The other thing is, of course, the reverse is if you have to do a neural network, then you better select, greater than 100, right? So that you have more features to work with. So that's one thing that I want to mention. Another thing I want to mention is called number of instances. It's this section down here. This number of instances, it means number of rows in your data sets. You download it, you load it up to Python, you do your usual thing, and you open up a table. It's like how many rows, and you want to be as many rows as you possibly can, hopefully greater than 1,000, if you want to do neural network. If you want to do a neural network model, this is a hidden rule, which I don't think it's proved yet, but people tend to respect that rule of thumb, and I'm going to tell you guys anyway, even though there's no proof, right? Typically in neural networks, every class that you want to predict, you want to have at least 1,000 samples. let's say it's two-class classification, right? Very simple, cats and dogs. You better have 2,000 pictures. If you're somehow less than that, then you need to rethink about your features, your models, and all that bunch of other stuff start happening. And these are problems you have to solve before you even touch the code, right? So it's not like you can't do it. It's a more challenging direction, right? So that's another thing, right? So right off the bat, number of attributes, number of instances, these two things you have to be aware of. If you want to do neural network, right, you better watch out for these thresholds. Okay. Other than that, you can pretty much do whatever you want. I don't particularly care which area, which field, data type. I don't particularly care about any of that. It just sometimes maybe you find data set that have a lot of strings, and it's not like a data frame that's all numbers. Then obviously you have to process it, right? And what that means is what? You have to slice the data, you have to recompile data, and do all that stuff, right? So let us know. That's going to be like a case-by-case base, depending on what project you're doing. Somebody asked a question, do we write it in TensorFlow? It's up to you. You can use scikit-learn. It's a nice package. And if you can find valid resources online, please feel free to use scikit-learn. You do not have to do it in TensorFlow. I know most of our class tutorial is kind of given and provided in TensorFlow, but you don't have to. So, yeah, so that's a good question. Yeah, you don't have to. All right. So that's the first source, right? First source, UCI machine learning. The second source is called Kaggle. This one I think is the most popular one that everyone has already heard of. You go to kaggle.com, right? Super easy, right? You click on datasets. That's the third button on the left, datasets. And then you see a search box, and then there are a bunch of datasets down here. The trending data just means whatever is trending right now. It doesn't mean it's a different concept than popular, right? Trending is like popular right now. It doesn't mean it's always popular. So people tend to click on the first line simply because of trending. And my recommendation is you can of course click on it, but read through, at least get a sense of what you're doing is what you're actually, what this data set is providing is what you're actually doing. And make sure those boxes are checked, right? Number of attributes, number of instances, and clean data, right? Like you don't want to open up data, it's like a bunch of strings, right? A bunch of like words and letters. Then you gotta process it. So that's gonna slow you down, right? We're talking about in 5 days deliverable, right? So you gotta beat that deadline. So that's one thing. You can click on it. My recommendation is you go to popular datasets. Popular datasets, chances are there are so many people have shared code online. So even if it's something that's a little bit out of the range and maybe looks a little bit complex and you have no idea what's going on, you can still find a source code and it should be able to get you started. Okay, that's probably one thing I would recommend, which is to check out these links. And I'm going to show you an example. Let's say I actually haven't checked out this one before, so this is completely new for me as well. So I'll click on that, open up a new tab. The first thing is I see data, and I almost make sure to read whatever's in the content, at least get a sense of the description of what the data is talking about, right? And specifically, what is the columns, okay? So columns, work year, okay, what is that? Experience level, okay, what is that, right? You want to get a sense of what this data is doing. Because data science job salary can be anything, right? You want to know what this data is providing, okay? So that's just a small caveat that really, I think, and again, this is not like I don't want to come here and say, okay, you guys absolutely have to read every word, right? That's not like kind of defeats the purpose a little bit. Of course, you guys can cherry pick a little bit and read the part that you find interesting that can help you tell a good story. I prefer that than I tell you to read this paragraph and you go ahead and read this paragraph, right? Does that make sense? So whenever you read through this what do you call this, about data set or content or whatever description that this Kaggle post is talking about, right? I always try to get a sense of what is it that I want to predict. Okay, let's say I read through this data set, and I already see a couple of things that might be interesting, right? First thing is, well, maybe some of the stuff here that's like strings, and maybe I need to do a little bit of processing. And I kind of get a sense of like a mental calculation of how long that takes, right? You have 5 days and you're submitting this by Friday. If this thing is going to take you 3 days, then probably that's not a good project, right? So that's kind of the story here. And the next thing is I want to get a sense of what to predict. Okay, so the salary is probably something that we can all agree on that it's relatively more interesting than all the other features in this data set, right? Like if I tell you, say, okay, I'm trying to predict company size, like you're gonna fall asleep, right? And I will say, okay, I'm trying to predict like employment type. And again, you're gonna fall asleep, right? Part-time, full-time, who cares, right? I care about money, right? So that's kind of the idea here. Like once you read through this, you should not need to download the data set to be able to tell exactly what is it that you're trying to predict. And that's important, right? If you don't even know what you're predicting, then you don't have a project. So the first thing that I want to identify is what is the feature, what is the column that I want to predict. Okay, and that's super important. So that's something I want to say first, and it goes the same way with Kaggle, goes the same way with the first one that we introduced, this thing, right? Use that machine learning repository. So with that being said, I think that's pretty much what we all have. That's important that I want to introduce. And then with that being said, I think I'm going to tell you guys one more thing that's called an TensorFlow datasets. TensorFlow Keras datasets. So I'm going to load this up and then I'll walk you guys through what's going on. So TensorFlow, fortunately, it offers this API allow you to download data, right? And we talked about a couple of data sets, and today we're also going to talk about new data sets. There are images, and based on different data sets, you of course gonna do a couple of things differently, right? So you either gonna build an image classifier, or you're gonna build some sort of logistic regression, or whatever, right? So that's gonna be something that is definitely important for you to know before you even talk about Python and who's doing what, right? You want to truly understand what that process is and how that's going to carry it out when you are working on your own projects. So what's going on here is this is actually an API that allows you to directly download pretty much any of these data sets. And you can essentially pick anything you want. Typically, what I realize that can happen is students tend to avoid projects that are like in class. I don't particularly know why. Like it's not like I said you can't do it, right? I mean, feel free to do whatever you want. But from the past experience, it's always interesting to realize that the things I talk about in class, people tend to stay away from that. Like for example, sometimes I talk about C410, right? Or maybe I talk about that data sets, or maybe I talk about that data sets as a regression tutorial, and then people tend to stay away from that. So I don't particularly care which data set you do, as long as you can tell a good story. Does that kind of make sense? So I just want to make sure that's completely clear, and you feel free to use whatever data you want. Oh, of course, that includes data set that we talked about in class, right? The only thing I would want to say is you obviously don't just copy the code from the class and then repeat what I said, right? You at least change a little bit. I don't care how much you change, but at least you change a little bit. That's probably the only thing I will say. In addition, you do whatever you want, right? This is a complete free world. Okay. Any questions? Any questions about projects? Any questions about data set? Now's the time. Any questions? Let me check the chat. Yeah, okay, so I think there are a couple of teams start to add me and Sam. Thank you for doing that. All right, awesome. Cool. So yeah, let me see. Is there a question in anybody else a question? All right, awesome. So I think that's pretty much all all I want to say about the projects. I think now everyone's being a team, and you know who your teammates are, and hopefully you guys can start tossing around like all these websites, all these links, just to see like what each data set doing, and then hopefully by the end of today, you guys can kind of nail things down and start a project. Oh, by the way, before I forget, somebody's asking me about a NASA data set. I know that NASA recently has some new discovery, right? Yes, feel free to, by all means, please, if you want to take a stab at that, definitely let me know how I can help. Just, I don't know how difficult that data set is because it's a new data set, right? They just literally published it. And let me know if you run into, whatever, like data processing issue, whatever issue that you might run in. My sense is typically whenever there's a new set of data released, either the data set is not clean or the data set is without labels. Okay, so you might have to like physically generate the labels yourself, which then raises the question, well, what is the machine learning process, right? Because if you're generating the label yourself, then what is it exactly you're learning from? Like learning from you or like learning from industry experts, right? So it kind of raises a little bit of questions in there, which typically I tend to avoid. Like I do the same as my work as well. Some people are saying, oh yeah, you got it. Just, generate the label yourself. Then my question is, okay, well, I don't mind spending, 2 hours providing the labels, but my labels don't have value, right? I'm a data scientist. I'm not a doctor, right? I'm never going to med school. I don't know anything about cells, genomics. I don't know anything about it. So if you ask me if this guy has cancer or not, I have no idea, right? So it kind of is a little bit even related to that. Of course, in healthcare, the stakes are a little bit higher, right? The diagnosis decision labeling is of course different than if you just open a picture and you're trying to label it's cats or dogs, right? It's completely different stakes at the table. So as long as the stakes are not that high, you feel free to find the data and label it yourself. Does that make sense? So now we're talking about, okay, generating your own data, right? You find the data, if it's new data, doesn't have any labels, and you want the labels, feel free to generate yourself. As long as we're not talking about like people dying, then I'm generally okay with you guys do whatever you want. All right, so that's that. And then other than that, I believe we are clear to pursue the next step. Let me just check my slide real quick. All right, I think we're good. Awesome. So, all right, let's come back to the material of the class. So let me do a recap. First of all, what has happened, right? Last week, we talked about linear regression. We talked about logistic regression. And then we did a code walkthrough, right? And I believe we spent 2 days on using TensorFlow to build different models. The regression model, this classification model. You can have 2, 3 layers if you want to, and so on and so forth, right? But we haven't really talked about the theoretical component of exactly how neural network works. You guys seen from the code, and maybe you generate some results, knowing that deep learning can do A, B, and C, right? But today, the first agenda is to kind of dive into deep learning a little bit deeper and walk you guys through each building block of what that part looks like. So before I do that, let me stop share and let me share my screen. I'm gonna have to go grab my iPad. All right, give me 1 second. So the thing about neural network is from before, we kind of walked through on a big picture, right? We know a linear regression model, and we found the math of logistic regression model. A logistic regression model is kind of like a transformation of your linear regression model, depending on different assumptions in the data sets. So one big problem is the linear regression model, or whether you're doing logistic regression model, it is always giving you fixed a number of solutions or fixed set of solutions, and they actually rely a whole lot on the features. And let me show you just quickly what's happening. So far we talk about um, linear regression model, and we also talk about logistic regression model. And the story are essentially kind of shares similar philosophy, right? The linear regression model, you have your y, and then it's like beta 0 plus beta 1x. And then for logistic regression model, we say, okay, it's a probability for each class. So this y is not going to work anymore because it's probability, right? It has to be between 0 and 1. So then we're like, okay, how do we do that? Well, let's come up with a p, right? And then let's come up with log odds, right? Or odds ratio. So p over 1 minus p. And then we say we don't like that because that's kind of like going too far off the range. We want something to be between 0 and 1. So then what do? Okay, let's transform. Right? Let's let logarithm. And then let's set this as the regression model. And then in doing so, you work on the math, da 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 da. Right? Turn out that this p is really 1 over 1 plus exponential. Now, of course, it's minus beta 0 plus beta 1x. And then we have a story, right? So what's the story? The story is, well, the linear regression, it kind of goes this way. It's a line, right? Let me redraw that because that's not a line. That's a line. And then logistic regression is kind of like this, but then everything is kind of rescaled to between 0 and 1. So what does that mean? Is this is 0, maybe this is 1, and then you draw a line. So let me try my best. It's going to look like this. Right, that's a kind of like a curve, right? So that's what we have so far. Now, one big problem with this entire field is this, right? Is the following. The result of how accurate you are, sure, it depends on the model, of course, right? But it also depends on your feature. Okay, so here, this x is exactly what your feature is. So all of the information that this outcome is allowed to learn, or whether it's this guy here that's allowed to learn, it all comes from this x here. If your x is messed up or inaccurate, then your final accuracy is out of the window, right? Nothing's going to work for you. So that's a problem. Okay, that's a problem. So then what you do is, okay, how about we use polynomials? And then we show you guys a polynomial function, right? So what you can do is you do plus beta 2 x squared. And then you do the same thing here, plus beta 2 x squared. And then you guys get the idea, right? Okay, if you want to do x squared, then why don't we do x cubed, right? So we have a beta 3 x to the power 3. And then so on and so forth, right? Now you get the idea. Right? This story or this conversation can continue forever. Right? You're not gonna see an end, right? Then you're gonna ask a question, well, how about 4? How about 5? How about 6? So there's no end to that question. Okay. So from there, people have done some sort of innovative discovery. People been using feature selection. People using like we talk about briefly. Hey, what if you get rid of this column, right? What if it's just a subset of 2 columns? Yeah, you can do that. You can have a try, right? So there are all these questions raised. And neural network, when neural network came in, neural network's like, okay, why don't we artificially represent the features by the neural network itself without having to feed into these x squared, x cubed manually. Okay, so people tend to miss this part. Neural network is fundamentally falling into this field called representation learning. So I'm going to write that down. This is actually an important keyword. So we're going to have representation learning. And on the representation learning, it's neural network based. Okay, so there's 3 things. The first one is called artificial neural network. This can work with any data. So you have some sort of x1, x2, doesn't matter. Coming here, there's going to be a black box f of x, and then coming here, there's going to be a y, some sort of prediction. Okay. So that's artificial neural network. This X can be whatever you want, right? It can be tabular data, pictures, categorical, multivariate, uh, text, right? It can be whatever you want. It doesn't guarantee accuracy, but it can be whatever you want, right? Then depends on the assumption in the data. We can also have convolutional neural network. So that's going to be one thing here called convolutional neural network. So I'll just say NN. NN means neural network. Okay. So this is for images. So what that means is you have a picture coming in. I don't know how to draw a picture, so I'm going to draw like a cat, something like that. And then coming here, you go to this F. And you need to say cat, right? That's classification. Or the extension of a convolution neural network is what we call the image-to-image model. So there's an extension here. Image-to-image model. And under image-to-image model, there's of course a bunch of other things, right? The easiest one is called the autoencoder. The upgrade of that is called the variational autoencoder. Whenever I AE, I meant autoencoder, so it's a same word here, right? And then outside of autoencoder, what else do you have is image segmentation, right? So I'll quickly draw what autoencoder is. This is the classification that your conventional neural network, right? You have X going in, make a prediction, very similar to linear regression and logistic regression, except that this F is very flexible. A second one is convolutional neural network. So what that means is your input is a picture. And the picture coming to this, you learn whatever you want to learn, you produce a label. It's a cat, right? And then you also have autoencoder. Autoencoder is about learning the data itself. So you have a couple of layers coming in, you reduce, and then you have a latent layer, and then you expand, and then this input and output is exactly X. So when you train it, you fit in the X for both the input and the output. So in other words, this kind of architecture is really about learning the original structure, or how do you say the internal structure of that original X. And this is going to be a field where you do not need Y. So you do not need, I'm running out of space here. So let me move this here. You do not need Y. There are some talks right now thinking about or trying to create the real artificial intelligence called artificial general intelligence. I don't know how much of that is fiction and how much of that is truth. But if that is truth, this is where you start. Okay, this is where you start. And the reason being, if I walk on the street and I see a cat walking past by in my neighborhood, I'm not gonna have to like open up a Wikipedia or open up a encyclopedia to look up a picture of cat and think about it a little bit and then say, oh yeah, that's a cat, right? I'm not doing that because that knowledge is innately solved by me in the past, right? I've seen this animal in the past. I know that's that, right? So in other words, somehow I can like if you give me if it's a new animal jumping out that looks like a puma or something, right? Let's say I don't know if that's a puma. I should still be able to tell that it's more like a cat than a dog, right? So that's kind of the theory here. So what's artificial general intelligence, AGI, right? It's referring to the type of machine learning technique, or specifically in this case, neural network-based technique, such that you don't really know the label, or you don't really need the label before you make a prediction. Okay, so that's what's going on. And the autoencoder is like the first step to do that. You can't really be telling people you know how to do AGI, but you have no idea what is autoencoder. Right? That's not going to make sense. Okay, so autoencoder is like the first step towards that. Even though it's like kind of like a baby step, but still, it's the first step towards that. Because somewhere down the road, you kind of need to say, okay, whatever this is, let's just abandon that, right? Because at the end of the day, it's still provided by human. It's not provided by machine. So if it's provided by human, then guess what? There's human bias, right? So that's what's going on. Okay. After auto encoder, you're gonna have image segmentation. So let's write that down. Image segmentation. And then the standard example is called unit. This is essentially a picture coming in like this, and then you're gonna have to shrink it. Oops. And then shrink it again, and then connect here, and then you kind of want to expand, and expand again. And then some of these layers, you want to draw some concatenation, and we're going to explain what that means. But for now, just think like that, right? Not only are you decreasing and increasing the dimension, but you also have these lines skipping ahead, right? This is called a unit. And what unit is doing is it's learning to predict the semantics level, what is different from the other region of the original image, or also known as mask. Okay, so this is learn to produce mask, where this is your original image. All right. So that's this type of neural network architecture. So I'm going to try to explain as much as I can. But of course, due to the length of the class, I'm kind of limited to explain all of them. But I'll try my best. So that's convolution neural network, and that's probably at the frontier of what we have today. Couple of famous important tools that people will do using convolution neural network. And then the last thing in convolution neural network, just to tease the idea earlier, somebody asked a question about GAN, right? This is called a generalized adversarial network. All right, so what this means is, or also known as GAN. All right. So what GAN is doing is, it is essentially taking something similar to image segmentation, such as autoencoder. It's taking something similar to that, but adding a new component to it, right? So you have some sort of picture. Let's say that's your image, and then I'll just draw like a square like this, and then you shrink just a little bit, and then shrink again, and then you expand it, expand again, something like this, right? This is kind of the idea where generalized adversarial is trying to take advantage of. Okay, so what GAN is doing is take this apart and treat it as two different components. Okay, so in order to do so, I'm gonna have to erase this part, and then we're gonna cut like make a cut in the middle. Okay, make a cut in the middle, and then what GAN is doing is, okay, it says take this, put it here, and then take this and then put it here. Okay, now I can get rid of this line. This is called a generator. Oops. Or you can just call it G, right? A generator is taking a noise, going into the model, and generate a picture. So image. Okay, and then this image is going to send through this thing here, and then come out with a score. So this is called a discriminator. Okay, so in other words, what does it mean? It means that one machine is generating a picture, and we take the picture, we throw that picture into the second machine, and the second machine is telling us a score in the end. And the score can, of course, go high or low, right? It's a number, right? It either go higher or lower because it's one number. If it's higher, then that means this picture is a good picture, or a similar picture, or that it checks, or that it's cats, and so on and so forth, depending on how you define the data. If it's a low score, then it fails, or this person should not enter in the door, or this person doesn't belong to this office building, or it's not a cap, right? So it can be high, it can be low. It matches certain definition of how you define what a similar picture is. So in other words, the high and low of the score, it really measures similarity. So score might not be too meaningful, right? But if I say similarity, hopefully that rings a little bit bell. Similarity, like that. And then, people get confused. What similarity we're talking about? Like, similar means A is similar to B. So what is A, what is B? Well, that's up to your definition. Right? It's data set. You choose a data set. You tell me what you want. You tell me what's A, what's B. And then the model says similarity. So that's complete up to you. Okay. All right. So that's a whole lot about image-based model, and all of that falls under the realm of convolutional neural network. That's kind of like a stretch to say that. If you want to be really careful of your language, I would probably call convolutional neural network as some sort of building block, and all of the tools that you learn in convolutional neural network should be able to guide you through each of these stuff, right? So I would probably want to make sure I learn this first, and then learn this, and then learn this, and then learn this, and then learn this. That's how I would do it. Okay. This way, if you're making a jump, right, you're like jumping here or something, you can do that, but usually what will happen is somewhere down the road you're gonna be like, wait, what does this mean? Okay, let me do some research. All right. So I'll give you an example. Let's say you're here, you jump here, and then somewhere down the road, something you don't understand, and then you're like, okay, what does this mean? Let me do some research, and then it turns out it's a problem here. So you're gonna have to come back and learn this anyway. So my recommendation is you take baby steps and you flush out all these models one by one. That's probably a more well-rounded strategy. Then if you make jumps, then your knowledge have these gaps in the middle. And when things go wrong, you're kind of like left in the dark, So that's what I will recommend. Now, of course, we're not stopping there, right? There's this thing called a natural language processing. So here we're going to say recurrent neural network. And this is pretty much used widely in natural language processing. Or also known as NLP. But then that being said, the language is kind of like a subjective choice, right? People do recurrent neural network in all sorts of different fields, as long as the data has timestamp in it, or time series data, right? You don't have to only do NLP. Although NLP is like a very big field and it is an interesting field, but you don't have to do that, right? When I say recurrent neural network, I'm talking about the neural network model that's sequential, that's trying to understand time series data. I'm not only talking about language, right? There's a difference, right? There's a difference. So this is obviously, if you want, you can say this helps understand language problem. But if you look at the technology itself, recurrent neural network can answer so many different other questions, right? It kind of is like this kind of a situation. It's like a belong to situation. Make sense? So that's kind of what's going on here. I just want to set that straight because NLP is such a big field that if you look at the papers, I can almost guarantee you the number of paper in NLP is much more than the number of papers using recurrent neural network to solve other problems, right? I'm pretty much willing to bet all my money on it. So people tend to think, oh yeah, therefore it's like this. Well, not really, right? Recurrent neural network can do a lot of other things. You don't have to work on language problem. So that's what I want to say. I see a team that's doing stock market. When we talk about recurrent neural network, this is the time for you to shine. Okay. This type of model is specifically designed to take care of time series data, not just language data, time series data. It just happened to be the case that language also has timestamp in it. That's why we treat language as time series data. Okay, so that's what's happening here. All right, so time series data, let's quickly go through what that means. You have an x, and then you have a timestamp, right, t. Okay, but this is kind of like a simpler way to describe what x is. Now, of course, this x can be, you can kind of call it t. Here you're gonna have an x t plus 1, and then here you have x t minus 1. All right, and we're gonna talk about how do we train a model to learn. Okay. All right, so first things first, let's go through the list. What we're going to talk about today is called the artificial neural network. Okay, it's going to be quite straightforward because you guys already know what's a linear regression. You guys already know what's a logistic regression. But this should be very straightforward. So the first thing I want to get set up is forward propagation. For forward propagation, kind of as what the name suggests, it goes forward, right? So what does that mean? Well, let's write it out. Let's say you have features. Let's keep things very simple. Let's say you just have x1, x2, and x3. That's terrible drawing. So x3. Three numbers, three columns, right? Three features. And the first thing about forward propagation is you need to go from x to this neuron, right? So I'm going to draw it up here because sometimes you can have more neurons. But I'm going to make my life easier. I'm just going to draw two neurons, so A1 and A2. So the first linear regression model, or shall I say the first logistic regression model is what? Is you have to go make or draw all these lines to connect each neuron from previous layer to each neuron in the current layer. Okay, so that concept is called fully connected. All right, so let's write it down. The first one is this, and then this, and this. And then you have a second line that goes from here, and then here, and then here. Okay, so in other words, you have a one logistic regression model for the blue model and another one for the green model. Okay, so we're gonna write both of them down. All right. So first things first, let's just take baby steps. This is blue color blue color W1, W2, W3, and then you have green color W1, W2, W3. So when you work out the math for these two neurons, you better write out all of them, right? So I'm going to try to keep things very straightforward. So I'm going to try to avoid that sigma symbol, but you can very well write it out as a sigma symbol, okay? So the first model is going to be A1. So let's talk about A1. The first thing about A1 is you need to throw that x1, x2, x3 into a linear regression model. So what that means is you're going to do this first. x1, w1 plus x2, w2 plus x3, w3. Okay. And then since it's blue, let me just mark as blue color. Okay, it's a blue model. And then what you're gonna do is you're gonna throw this into some sort of activation function, right? So we talked about the field. What is activation function? Activation function. So we talk about a field, right? The first thing is ReLU. ReLU, you throw the input z inside the function, and it gives you maximum of z and 0. So what that means is you take the z compared to 0. If it's positive, you let it go. You don't change anything. It's a z by itself. If it's negative, you replace it by 0. So in other words, if you draw it out, it's going to look something like this. Like that. And let me use different colors so we can differentiate like this. Right? And this is exactly what ReLU is. So in other words, ReLU doesn't like negative values, right? If you're negative, we replace you as 0. It's like nothing happened. So it doesn't take negative values. And then people are like, why do we want to do that? Well, it's not a must, right? It's a choice. Right? So once again, it's a choice. All activation functions are choices. Even though some activation functions are designed for certain tasks, and there's few rule of thumbs, maybe like 2 to 3 rule of thumbs, but on a high level, activation function is like subjective choice. Okay, so I just wanna throw that out there. Some other functions, sigmoid. Sigmoid, you guys know exactly what that is. It's pretty much what we talk about in logistic regression model. So sigmoid, you throw that in there, it's exactly the same function. 1 plus exponential minus z. So this function is exactly the same as this function here. So this is also called sigmoid. Yeah, so I just replace z with, I'll replace the input with the number z. That's it. That's all I did. This entire form is exactly the same, right? There's also softmax. Softmax, you can throw a z in there, but it's dependent on different classes, right? Because it provides a distribution. So we're gonna talk about this in just a sec, because that's kind of like used in the very end. But for now, the ReLU and sigmoid should be able to take care of a lot of things. So from here, you can do ReLU, you can do sigmoid, all that's up to you, right? It's completely up to your choice. I'm gonna make things simple. I'm just gonna say, hey, let's throw that into ReLU, right? Let's do that. And then this is gonna give you either this number by itself or 0, right? So it's gonna give you something. Let's call it alpha 1, okay? So this is gonna give you alpha 1. And then that's A1, right? Now you work out A2. So A2 is the exact same thing, and I'm just gonna save some time because there's no point like repeating this. X1 W1 plus X2 W2 plus X3 W3. But then the problem here is this is a green model, right? So it's the other 3 W's, right? So this is W, 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 and then the top one is gonna be blue color. So this is blue W 1, 2, 3. Make sense? So this way, your alpha 1 and alpha 2 should be different numbers. Right? So that's a problem, right? That's a point. Now we're not there yet, right? We need to do something else. And then here it's complete up to your own choice. If you are in a regression problem, then you just do one neuron in the end. You just say, hey, we have a y, done. If you are in a classification problem, then you need to go through 2 or 3 neurons depending on how many classes that you're doing. Okay, I'm gonna write both of them for you guys. So let's make a duplicate. Let's do y first. We'll take a break and then we'll come back. We'll pick up on that. So I'm just gonna do y first. Let's make things a little bit easier to understand. So I'm gonna use a different color like this, and then I'm gonna say W1 and W2. So now you guys get the idea, right? Now it seems very simple. So what is your y? Your y is going to be A1, oops, let me write here. A1 times W1 plus A2 times W2. Whatever output that is, right? That's going to be the final one. So you can kind of call this alpha 3, and this alpha 3 is going to be your final output. And then you can kind of treat this as the end of forward propagation. So when we say forward propagation, we are referring to exactly these formulas. Okay. Now notice that what do I mean by representation learning? What is the represent here, right? What are you trying to represent? The representation learning, the concept of represent, means that the information is not directly coming from the features. Right? It's not the x1, x2, x3. It's not. The final prediction is coming from what the model is representing x1, x2, x3, or what the model thinks it's representing x1, x2, x3. It's not x1, x2, x3 by itself. Okay, this is the key concept for neural networks. So it's a representation learning. It's not learning from x1, x2, x3 directly. It's learning from the representation of x1, x2, x3. So what is representation? Well, you have an A here, right? The A1, A2, this is what the neural network thinks what x1, x2, x3 is. Okay? So when it's making predictions, it's not making predictions from x1, x2, x3. It's making predictions from what the model thinks they are. Does that make sense? That's the difference here. Okay, that's the difference. So with that being said, let's take a break here. Let's come back in 10 minutes. And then we'll pick up from here, and then we'll jump right into classification. So take a break. Yeah, I'll see you guys in 10 minutes. Okay, so let's get back to the topic that we are left off from earlier session. So far we talked about where these formulas come from and what these lines mean, right? We use three different color codes: blue, green, and whatever color that is, pink, and they all mean certain things. The blue is one model, the green is another model, and the pink is another model, right? So now here's a caveat. What if I want to have a classification problem where the output of the neural network model is in different classes? Now, of course, this model is not going to do that for me, right? You only have one output, right? One output, just y, and that's it. But whatever y is, that's just one number. So you can probably take a guess that this y, it's not going to be a classification setup, right? Whatever this y is, it's going to be a numerical value, and it tackles the tasks such as predicting housing price or something static, right? Like a numerical value that's kind of like a continuous number. So that's the problem, right? We want to turn this into something that is in classification setting. So here's what we're going to do. I am going to use the magic trick of iPad, and I'm going to make a copy and put them side by side. Yeah, you know what? Let me try this. All right, so that's it there, and then I'm going to put another copy, exact same duplicate, down here. Except that I'm going to change a few things. Boom. Okay. So now I'm going to change a few things. Now, instead of just y1, I'm going to move them up a little bit. And then we're also going to have a y2 somewhere here. So this is going to call y1. This we're going to call a y2. And then, of course, we're going to give a slightly different color. Let's say orange. And then we're going to draw one line here and one line here, right? And you probably guess what I'm about to do. I'm going to call them orange color W1 and orange color W2. So in order to complete this graph, now I need to write one more equation, okay? So let's make sure that this is notation clear. Y1, that's Y1, that's coming from the pink color. And now I have orange, which I'm about to write here. So let's write the orange color coding here. So it's going to be the same model as the Y1, right? The same model. So we can really just copy it down here. So I'll just copy real fast. Now, of course, that's going to be called L4, right? And then you have A1, W1 plus A2, W2. Now, these weights are color coded. So let me make sure that's up to date. This is the pink color, W1, W2. And we have the orange color, W1, W2, so that you know these are different W's and they're different values, okay? So now with that being said, we're at the final step, right? Now you can make a softmax function, okay? So what's gonna happen from here is you're gonna send this y1 and y2 into a function called a softmax function. So basically it's something like this, softmax. And then I'll just draw a box surrounding it. And then this is going to give you a vector, right? A vector that is probabilities. So since they're probabilities and they're technically speaking different numerical numbers, so I'm going to give them a different name. I'm going to call them P1, P2, okay? P1, P2. All right. So now let's work out what this, how this math works. So of course, this is also your final number. But notice that these two numbers, they are not in probability, right? This can be 4 and this can be 10, right? Some whatever arbitrary number that you like, right? But they're not going to be probability. They might be, one of them might be fraction, but you can't guarantee both of them are fraction, and you can't guarantee that they sum up to be 100%. So that's why we have to do softmax, because softmax guarantee those two conditions, okay? So let's write that down. The problem here is, what's the issue here? The issue here is not probability. And the second one is doesn't sum up to be 100%. Right, that's a problem. So softmax function takes care of these two problems. Okay, I'm going to do that right now. So softmax is you write a formula down first, and then you plug numbers in. Let's say this is exponential. Actually, let me be a little bit careful. Softmax of z1 is exponential z1 over exponential minus z1 plus exponential z2. And then if you know calculus and you're comfortable with the sigma sign, you kind of get the idea, right? Okay, no one's gonna write it out, so people are gonna summarize it using sigma. So exponential minus 1, and then this is going to be summation, and then you can say k from 1 to 2 exponential minus zk. All right, so that's the sigma, the softmax function. But this is just one of them, right? We have two neurons in the end, right? So now I gotta write the other one. So softmax z2 is going to be exactly the same thing, right? Is the only thing difference is you switch the 1 to 2 on the top of the fraction. That's it. That's the only difference. Over, and I'm not gonna copy that again, so I'm just gonna say k from 1 to 2 exponential minus zk. All right. So now you guys get the idea, right? Since the bottom of the fraction is two numbers add up together, then it means what? It means it has to be 100%, right? So I'm not going to write this down, but you can kind of check real fast. You can say exponential to the, let me write a different place. Exponential to minus z1 over exponential to minus z1 plus exponential to minus z2 plus exponential minus z1 plus exponential minus z2. This is exponential minus z2. If you add them together, the bottom of the fraction is the same, right? It's the same. So you connect this line and just plus write add here. Then you're gonna realize it cancels out, right? So the top and bottom cancels out, and you're gonna end up being 100%. Okay, so hopefully that's clear. If that's not clear, let me know and I'll write it out for you. All right, let's make sure there's no questions. Okay, I think that's good. We don't have any questions. Awesome. All right, so this helps us finish forward propagation. You have information going in, and you have two scenarios. If it's a regression problem, you have one output. So let's put a remark. This is going to be a regression problem. And of course, if you're two neurons, then it's going to be a classification problem. So this is going to be a classification problem. And now you can zoom out, then that's the difference, right? So information come in, this is X, information come in. If one neuron is a regression, the same information come in, if you define two neurons, that's a classification problem. Okay, so that's the difference. Now we have finished forward propagation. The next step is backpropagation. Okay, and we're gonna take baby steps right out what that means. So let me go to new page, and then we're gonna write backpropagation. All right, so I'm of course gonna cheat again. So I'm gonna take this graph and I'm gonna copy and paste it down there, so I don't have to draw it again. All right, paste, perfect. All right, I'm gonna put it here. Awesome. So we have this graph. We know how it works from left to right. Now we need to go back, right? So if from left to right means forward, then from right to left means backward. Okay. So backward direction is really like this direction, from right to left. And we're gonna talk about exactly what that means, okay? So there's this thing called the gradient descent. It's a type of algorithm that help you to find the local optimum, or the lowest spot, if you will, okay? So think about a very simple scenario. So this is basic math. Think about a very simple scenario. Let's say x squared. Very simple, right? X squared. X squared looks like a U shape, right? That's what x squared means. So let's draw that out. That's x. Maybe that's your bar here, and then you draw some sort of U shape. Except that that's 0, right? Okay. That's your x, and this is x squared, right? And the gradient descent means that it is an algorithm that it doesn't matter where you put me, I'm always able to find this spot down here. So that's what the gradient descent algorithm do. Okay, and I'm gonna walk you guys how to do that. Let's say, let's say I'm here. Let me switch a different color. Let's say I'm here. The first thing that it does is going to calculate the gradient. Okay, so if the red line is here, then the gradient is like this one, right? Basically, that means the slope. And it's not just any slope, right? It's a slope at that spot. Because if you change the dots, the slope changes, right? So this slope is going to be positive number, right? So slope is a plus. That just means the sign of the slope is positive. And the good thing is, gradient descent always subtract what the slope is doing. So the slope is positive, you subtract a positive number, then you go left, right? Because subtract means you go left. So minus plus, this gives you minus. Minus means what? Go left, right? So this is go left, right? Now, go left means what? You do this way, right? But you need to go left along the curve. So what that means, you do this. And now you're here. And then you do the slope again, right? Now this is your slope. It's also a plus sign, right? Because slope is still go up. So this is a positive slope. The sign is positive. So you minus a positive number, you end up being subtracting the number, right? And that means what? Go left. Okay, so this is also go left. And then so on and so forth, right? You guys get the idea. Okay, go left means this. Now I'm here. I do the slope again, positive, go left. Do the slope again, positive, go left. Until I hit the spot, right? So that's gradient descent. Essentially, in a nutshell, when your x or when your slope is positive. Now let's work out the other side, right? We haven't talked about this side. So let's work that out. Let's say you put me here. First thing first, let's do the slope. What is the slope? Slope is this, right? So it's not positive, right? It's negative, right? Because it goes down, right? It's negative. So whatever this line is, the slope is negative. So minus. So recall what we said, right? We always subtract the gradient, subtract the slope. So the name of the game is subtract slope. So when we're on the right-hand side, subtract a positive number means minus, so go left. But if we're on the left-hand side, subtract a negative number means plus, right? So you go right. Okay, so let's write that down. Let me give it a different color. So minus, minus, that means what? That means plus, right? So that means what? Go right. Okay, so this is go right. And then you do the same thing, right? If you go right, it means what? It means you're down here. And then you're here. You do the slope again. It's a minus. Minus, minus, that's plus. So you go right again. Go right? So then you're down here again, and then now you're here, you do the slope again, you go down again, and then so on and so forth until you hit this spot here, right? So it doesn't matter if you're on the left-hand side or you're on the right-hand side, you can draw me off anywhere on this x squared function. I have no problem finding this optimal point down here. So let me give a different color. So this spot here, this is optimal. Or sometimes people say best. Or sometimes people say lowest. Right? They're essentially referring to the same thing. Right? The optimal point, the best point, the lowest point, right? And guess what? In machine learning, that x squared is your loss function. Okay, why do I say that? Well, recall in the beginning, in linear regression, that's a typo. In linear regression, what's loss function? Well, loss function is this, right? And then equal to what? Some sort of summation sub index I, yi minus yi hat square, right? Well, you have a square, right? So you're like halfway home. So you have a square here, you have a square here. Then whatever this is, it's like something square, right? So it has to be this way. Right? The formula has to look like this. It may not look like a perfectly U shape, but it has to look like this. It has to go down and go up because the square is here, right? It has to be this shape. So if it's this shape, then we have a story to tell, right? You drop me off any point, this algorithm is always going to converge. Okay, so that's how things work. Of course, this loss function is kind of like arbitrary choice, right? I'm in linear regression problem. I want to predict something continuous. Therefore, I use loss function. Right? It's not an absolute science that you have to do things this way. It's just kind of like, well, certain assumption, we don't want to violate that, right? Because that's what data look like. But if you truly want to violate those assumptions, that's fine. Like no one's gonna say, like if you're in a classification setup and you want to use loss function that's like those that people use in regression problem, feel free to give it a shot. The code will still run. You're just gonna have to check the performance to see if it's good or bad, right? So all of those are complete up for grabs. Open table, open debate, right? I want you guys to open your mind. So feel free to take the shots. Feel free to try things out, right? So now, with that being said, we can write out the formal statement of this algorithm called gradient descent algorithm. Okay, so let me write it down here. Right, so we're gonna say gradient descent. All right, so gradient descent really is just 3 steps. First is you need to know your loss function. So define loss function. So this calligraphic L, right? YY hat, right? Whatever this is, right? Complete up to you. Depending on your choice, depending on what the data look like, depending on the real world situation. Okay. Now, with that being said, you compute gradient. Now, when I say gradient, people get confused, right? What is gradient? Gradient is just a slope. It's kind of like a mathematical way of saying slope, except that in machine learning, oftentimes people have different variables, right? Different input features. In this case, we have what? X1, X2, X3, right? So slope doesn't really tell the story because slope assumes you're one-dimensional. Otherwise, you don't have a slope, you have a plane, right? So if I say slope, what is the assumption? The assumption is it's a line, okay? How do you draw a line, right? If I give you an X, you can draw a line, right? But if I give you a plane, then if I give you like a three-dimensional object, then you're not gonna have a line, you're gonna have a plane, right? So think about it this way. What's the upgrade of this, right? You can have a three-dimensional. I'm not even sure if I can draw this, but I'm gonna try my best. So it's gonna be something like this. And then you're like some weird three-dimensional shape, right? Um, um, kind of like this. Oops. I'm not sure if this makes sense. I kind of like this. And then you have all these surrounding circles. So this is like the best spot down here. I use the same color so people know what I'm talking about. This is the best. And then as it goes circle, it kind of like fans out and it's like go up. So if you're somewhere here, then you gotta go this way and then hit the spot. Okay. So in this case, slope doesn't mean anything, right? Because when you're at this spot, your your quote unquote slope is gonna be a plane, right? It's two-dimensional. It's not just one dimension. So you can't call it slope, right? You have to call it gradient. So that's why people use the word gradient. Gradient doesn't subject to dimension. You can have x1, x2, you can have x1, x2, x3. It's all called gradient. But if you say slope, this is not a slope, right? I can't draw a slope, right? You know, this is it's a plane, right? It's a tangent. It's a tangent to the loss function. Okay. So you won't have a line, right? You can't just draw that. That's not gonna make any sense, right? Because it's a plane, right? So that's what's happening here. That's why people use this word slope, right? All it means is you're taking partial derivative. You know, you're not subject to which dimension you are, and that's it. So typically we use this letter. This is called a nabla. Okay. I think I mentioned it in the beginning, but I'm gonna say it again. Nabla means this. It's a Greek letter. It basically is an upside down triangle. It's kind of exactly like delta, but you like do like a mirror reflection, and that's what nabla is. Of course, you want to take a nabla of your loss function. So if your let's keep things simple. Let's say you're here, okay? Let's say you start from here. When you do gradient, you're doing gradient with respect to W1 and W2. Okay, so I'm gonna keep things very simple. I'm gonna write it out. I'm gonna explain it. So when you do gradient, you are doing a pair, right? Because you are doing gradient with respect to each parameter. So you're gonna do something like this: partial, partial, W1, your loss function, and then partial, partial, W2, and your loss function. Now, of course, this is a vector, so it's gonna look like that. All right, so now I write this down first. Now let's talk about what this means. Okay, so very high level, right? This is gonna be a different color, so I'm gonna try to use. I'm gonna try to use different colors. So we're gonna call this draft. All right, very high level. If you have 2 times W1 plus 3 times W2, let's say that's it. This is the formula that we're looking at. We're not going any more complicated, right? That's it. This is a formula. Very simple. Now, what is the gradient of this? Right? You say gradient of something, right? Well, following the formula, we need to do two things, right? We need to do this guy, and then we need to do this guy, right? We need to do two things. So what this means is partial, partial, W1, and then whatever's in the middle, right? 2W1 plus 3W2. And then you can write it out this way: partial, partial, W2, 2W1 plus 3W2. And it's a big vector, right? So you need to take partial derivative, or basically take derivative with respect to each W. When I say partial derivative, I meant taking derivative with respect to each W. In this case, we have 2W. Why do I say 2W? Because in the graph, when you go back, that's 1, that's 2. There's only 2 of them in the graph. If it's 3 of them in the graph, of course you do 3 of them, right? But for this case, let's just keep things simple. Let's say do 2 of them. So then in this case, what do you have? That's 1, that's 2, right? And then next thing is to take derivative, right? And it should be very simple. So what is derivative of this? Well, it's W1, right? That's with respect to W1. That's why I said partial W1. So what this is, no one cares because it's considered as a constant. With respect to W1 means I'm fixing I'm fixing everything else, even though it's a variable in the beginning, but I'm fixing them constant, just temporarily. And then I'm only allowing W1 to be the changing factor here. And I'm taking derivative on that. So then it's left with just 2W1, right? So if you have a 2x, what's the prime of this? It's just 2. That's it. That's all there is. So then let's write that down, right? 2 plus 3, well, that's gone. So this is just 2. Simple, right? 2. And then comma. But we're not done yet, right? There's the other half, right? So this way, you're taking derivative with respect to W2. So W2 is this guy here, right? So everything else, even though in the beginning it was a parameter, it's changing, but temporarily we're taking derivative. So we're pretending that this is a fixed constant, right? We're pretending this W1 is fixed. The only changing factor here is W2 because we are taking derivative with respect to W2. So if this is a constant, then they're gone. It's just 0, because it's not changing, right? The derivative is 0. Then you're left with what? You're left with 3W2, right? And that's simple, right? What if we give you 3x? What is the prime of this? It's just 3. That's it, right? So then it's easy. Then what's the derivative? 3. Boom, done. That's it. That's all you need to know. Simple, right? And then this way, you know exactly what this is, and you know exactly what this is. You have two slope, right? One slope is with regard to W1. The other slope is with respect to W2. It just in this case they're two-dimensional, so overall we don't call it slope, we call it gradient. So once you have the loss function, you can take the slope, right, with respect to each dimension. You're gonna get a gradient. And then the next thing is to gradient descent. Okay. So let's write that down. So last step, 3. This is called gradient descent. All right, so gradient descent is like this. There's a step called S, and that step is going to be what you track. Okay. So at each step S, you need to update the weight. Okay. So you update your weight. In this case, I want to be a little bit careful of the weight here, since the gradient descent is built on each and every small, I can call it linear regression model. That's why when I say one gradient descent algorithm, it's actually just one of these components. Okay, we haven't got into this guy and this guy yet. Okay, so right now we're only in this like microscopic world, just like this part. Okay, so now gradient descent, you want to update the weights. So you say update the weights. Okay, so how do you do that? Well, we need to write this out, right? So the name of the game is subtract slope. So that's a key idea. And if this is a key idea, and that means wherever I am, I take a look at slope, I go back. I take a look at slope again, I go left. And then I go left, I go left. That's because of what? Because you're subtracting something that's positive. And the other side is a reverse, right? You're subtracting something that's negative. Then you plus, that means you go right. Okay? So we want to write this in a simplified way, in an elegant way. Okay? So now I come down here, I say, okay, the W that we're talking about here, W, let me denote. W vector as the set of W1, W2. Now I want to be a little bit careful because this is small model here, right? So I want to use different color coding. This is this color, and this color. All right. So then, when I'm updating W, I need to have a subindex S that tells me which step that I am. If your first step, then of course you are still in the beginning of the game. You haven't finished yet. right? If you're like step 1,000, then you better get somewhere down here, right? Otherwise, something's wrong. So the step is an important mark to help us indicate where things are. If it's step number 1, then maybe you're here or maybe you're here. If you're step number 10, let's say s equals to 10, then you better be somewhere down here, right? Otherwise, you're not moving at all. If you're step 20, let's say s equals to 20, then you better be here or here, so that I know that you're going to the best spot. Now, if that's not happening, then something's wrong. Okay, so step is going to be important. So let's write that down, step. And then this is updated by the previous position, s minus 1, and then minus, this is called eta, and times nabla of your loss function. So let me write it down. Where eta, this means eta, is equal to 0.001. Usually it's a small number, so I'll say usually a small number. And then oh yeah, that's it. That's all the notation there is. All right, so that's it. That's the full scale of a gradient descent algorithm. So after this is done, you're going to realize that, oh, wait a second, we're only talking about the pink color, right? That's all we're talking about, the pink color. So after you do this, you only have updated W1 and W2 with the pink color, right? Which means you're only here. And then you need to do for blue color and then for green color. So what is backpropagation? Backpropagation is you do gradient descent and you propagate backwards at the layer level. Okay, I'll repeat that again. What is backpropagation? Backpropagation is gradient descent, but you go backwards and you propagate it at the layer level. Okay, so that's what it means. So in other words, if you go to this, you're only gonna update these two numbers, and then you're here, and then you have to update this, and that's considered one epoch. So that one for propagation and one's all the way back, which have in this case 3 gradient descent, right? That will complete one epoch. So this way, it completes one epoch. So already here, okay. So 1 epoch equals 1 forward plus 1 backward. All right. Okay. So with that being said, that's everything about gradient descent, but on linear regression model, right? Sorry, on a regression problem, not just linear, on a regression problem. In a classification problem, of course, this is gonna be slightly different, okay? And we're gonna take a look at the loss function in just a sec. But let me take a quick pause. Any questions about this part here? Any questions? Let's see. Anything on Slack or anything on Zoom? Any questions? All right, perfect. So yeah, let me know if it's unclear. And I want to give you guys one more tool, which is about let me just open that slide just to remind myself as well. All right, let's see. All right, so now I'm gonna wrap this lecture up with a final piece of puzzle. It's called a cross entropy loss function. And the reason I introduced that is because in the beginning we talked about 2 scenarios, right? One is a regression problem. It has 1 neuron in the very end. But if it's a classification problem, you have 2 neurons. 2. When you have 2 neurons, okay, you are predicting a probability. Right? Why do I say that? The reason I say that is because we go through the softmax function, and this gives us two probability, and they sum out to be 100%, right? So if this is 30%, this has to be 70%. It has to, right? And that's going to give us a different setup. So the original whatever square loss function in the linear regression model, that's not going to work. Okay. So now we need to introduce one new piece of puzzle, which is called cross entropy. So I'll write that down. So I'm gonna just cheat and copy this thing, and I'm gonna paste it down here. I'll put it right here. All right. So the gradient descent for a regression problem and for a classification problem is exactly the same. Okay. The only thing different is the loss function. So I'm gonna write it down here. Let's see. I'm gonna write down. Let me move this up a little bit because I'm running out of space. I'm gonna write it down here. All right. So this is a loss function. Y hat, right? And I'm gonna write it out first, and then I'll explain what it means. So we have a minus sign. You have 1 over n, and then you have summation, and then you have I from 1 to n. This I is a rounding index tracking which sample that you're talking about. And then in here you have yi log yi hat plus y minus yi log 1 minus yi hat. All right. And I'm going to draw a graph just to remind people what the loss function is doing. So first of all, you need to understand what is a log function, right? Like a logarithm function. So if you draw a logarithm function, it kind of looks like this, right? Something like that. But notice in this case, what do we have? We have a minus sign here, right? So this is not going to work, right? You got to flip it. So you can do a mirror reflection. So I need to control Z and get rid of that. Now, whatever this thing is, it looks like this. Oops, I got it right now. Does that kind of make sense? So basically what that means is, if you go to the left, it will give you a large number. But if you go to the right, and specifically here, this spot is actually 1. Let me write it down here. This is actually 1. This is 0. If you go to the left, meaning you go close to 0, it's going to be a large number. But if you go to the right, then it's going to be almost nearly 0. And if you go past 1, that's going to be exactly 0. And why do we do things this way? Because the original model gave us a probability. Probability means what? It has to be between 0 and 1, right? So this input range here from this input range here, that's from 0 to 1, makes sense because that's exactly the output that we need that goes inside of this loss function. So that's why we chose the logarithm. Okay, this is the interpretation on a high level. Whenever you guys learn statistics in undergraduate school, you guys are gonna learn statistical inference, and this is a thing called a likelihood function. Okay, this loss function is coming from exactly that. Okay, but I don't want to turn this into a stats class. So for now, the assumption, just bear with me, and the assumption is we want something that's 0 to 1, and we're talking about probability. So if you give me like a straight line, or like if you give me something like this, that this is 0 and this is minus, this is plus, I don't know what you're talking about, right? It's not a probability. Okay, but if you're doing this way, okay, then we have a story, right? You know, this is a probability. This is 50%. I know exactly what that is. Okay, so if you give me something like this, who knows? This is 0. This is maybe 10 here. This is maybe minus 5. It's not a probability. I don't know what you're talking about, right? So that's why we chose a different loss function. Okay. So here we say the premise is assumption. It has to be probability. And this it means the output from neural network. Sure, I wrote two letters NN, that means neural network, okay? So you do a neural network, you have some sort of output, it's a probability. Then what? You do a loss function, right? What's your loss function? It's this. It's a logarithm transform, right? That's a loss function. All right, so with that being said, now let's take a look at the actual function, right? This is the actual function. Of course, that log here, you know what the log look like, it looks like that, right? So now, what's the story here? How do we know your model is good and your model is bad? How do we know that? Well, yeah, if you look at this case, if you give me a low number, this is a low number, or if you're here, this is a high number, then I know what you're talking about. I know exactly what you're talking about, right? This is bad, right? This is the sad phase. Sorry, the reverse. If you're here, this is a low. This is a happy phase because your error is small. Or if you're here, your error is high. That means it's a sad phase. It's bad, right? So if you're low error, good. If you're high error, bad, right? That's clear, right? Low, high, very clear. But this is not that clear. Okay, we need to work it out. So how do we work it out? Well, you need to come up with 4 different scenarios. So I'll write it down. All right, 4 different scenarios. I'm only going to talk about the first 2, and I'll let you guys work out the rest. Okay. 4 different scenarios. 1, 2. Now, of course, there's a 3 and 4. But I'll let you guys work it out. All right, so I'll talk about the first one first. The first scenario is when you predict the probability that is small and the ground truth is 0. Okay, I'll write it down. So the first premise or the first scenario, let's say scenario. yi is small, y is 0. So that means what? That means you're good. Okay, if you tell me that your prediction is here, like 0.01%, right? A small number. And then the class is 0. Then you good job, right? It's a very close job. That's a good job. Okay. So let's work out the math. Why is a good job? So how do I know that's a good job? Okay. Well, let's work it out. So let's say, where are you? I'm gonna write like this. Right. So take a look at this. If y is 0, what will happen? Okay. If this y is 0, that means this is 0, right? Because that's y. That's where y is. So if that's 0, anything times 0 is still 0. Then this goes away, right? This complete goes away. So you don't have to take a look at this. It's 0. So then you're left with what? Then you're left with this guy, right? So let's write that down. 1 minus 0 log 1 minus yi hat, right? And then what's happening here is, well, 1 minus 0, it's nothing, right? It disappears. So I'm going to erase that. Now you're left with just log 1 minus y. Make sense? Now you're like, okay, the one minus y is kind of like very close to 1 because I told you that yi is small. I said it's small. Small means what? Small means you can pretend that this is 0.001. That's what small means, right? The least you can go is 0 because that's a cutoff. This is the cutoff. So this means it's small. That's the only range we are allowed to, right? The small one is 0, so small means close to 0. So if that's the case, then here you're going to be left with log 1 minus 0.001, which means what? Log 0.999. And we said in the beginning that we have a minus sign here, right? So we should probably add that back in, right? Minus, minus, minus. So where is this on the graph? It's here, right? It's exactly here. So let's write that down. Minus log 0.999. Right, that's where it is. Okay, that's the value. Okay, that's the vertical value from the function. Which one? It's a small number, right? So it's a small number. And hence, it's a good model. Okay? If you are guessing 0 or close to 0, and your actually class is class 0, of course, you're a good model. How do we know that's a good model? You work out the math, right? That's the math. Now, hopefully this is very clear, okay? And then, of course, now you guys get the idea, right? There are 4 scenarios. Why do I say 4 scenarios? This is small, this is 0. Or this is small, this is 1, right? Or this is big, this is 0. This is big, this is 0. Or this is big, this is 1. Right? There are 4 scenarios. 2 and 2, that's 4, right? So then you can work out the rest of the math. You can say, hey, yi hat is small. But in this case, y is 1. So y is 1. And then you're probably going to be like, okay, this is going to be a bad model, right? We know off the bat, okay, this is definitely not right. If this is class 1 and you're like, okay, the probability is class 1 is 0.1%, of course it's a bad model. But how do we know that's bad, right? What's the math here? Well, let's show you the math. So the math is going to be, you have to work out what does this 1 mean, okay? This 1 means your y is 1. Well, if your y is 1, then this is 1, right? 1 minus 1 is 0. So this is 0. So what that means is under this scenario, you don't have to look at the second term because the entire second term goes to 0. So then you're only left with this. Okay, so let's write that down, right? So this is what? This is yi log yi hat. And then this yi hat is 1, right? So it's like, it doesn't do anything. So I just erase that. And then now you have, don't forget the minus sign, right? The minus sign is here. So let's add that back in. And then you have minus log. And then here, I said yi is a small number, right? This is a small number. So small number means what? You give a small number, right? yi is 0.001. Yi hat is 0.001. It's a small number. So yeah, you plug it in, right? Small number, 0.001. All right, where is this number on the graph, right? It's going to be a small number, so it's going to be like somewhere here, right? 0.001. So like here, right? I probably need to draw a longer function like that. So then you are exactly here. This is a large number, right? This is a large number. So exactly what that means is this is going to be a bad model. And the one down here is going to be a good model. Make sense? So that's how I know which one's good, which one's bad. Okay, so once again, we work out 2 scenarios. So what are the 2 scenarios? You are guessing a small probability, but if the y is 0, you're good to go. It's a good model. And once again, the second scenario is you're guessing a small probability, but the class is class 1. Then that's a problem, but the model is bad. Okay, it's not accurate. So what do we mean by not accurate? Like what context are we communicating here? Well, we're talking about this kind of language, and the number here for this particular loss function is small. And if this is small, then it's a good model. Or if this is large, then it's a bad model. Does that kind of make sense? Any questions so far? Good. All right. Cool. Awesome. Let's take a break. It's kind of like a little bit of a mathematical technicality. So let's take a 10-minute break. Let's come back and we'll look at the code. So yeah, take a break. All right. Awesome. So this is the class folder, and right now, let's see. So I think this is the so class notebook is here. I'm probably gonna save what I'm doing in here. and we'll just keep writing this. Today is 25th, so we'll just save it here. Today, the rest of the plan is this. So, we spent like a whole lot of time today talking about theory, right? And the reason I do that is because, well, A, somebody asked a question. B, I want to make sure that you guys are solid on the foundation. And the reason I say that is because oftentimes students come back and they're in the middle of their project or they're in the middle of coding something, and then they're like, okay, I don't understand what loss function means. Well, this is why, right? This is why we do this up front. So make sure everyone's on the same page. Because it's really easy to go through code, and I give you the code, you run it, and then there's some output. Maybe it works, maybe it doesn't, right? When you're trying to debug, you're not in the mindset of trying to understand the model, okay? You could very well run through the code without understanding a single thing about the model, as long as you're like a little bit, had a little bit hands-on, you have an engineering experience, you're gonna get a code to work. I want to try to avoid a little bit that mentality, because I know in the long run that would do bad for you than good, right? You want to understand absolutely what each line means, not just from an engineering perspective, but also from mathematical perspective. So that's why we're doing this. Okay, so with that being said, first things first is we're going to quickly run through artificial neural network on a code basis. Of course, you guys have seen all this before. I'll just quickly go through it, but I'm going to pinpoint a couple of pain spots for you guys, especially in the data science project. Okay, so right now it's going to be slightly different than from last week. Last week we used the dense layer, right? You guys know all of that. In like regression problem, in classification problem, and so on and so forth. Right now I'm going to pinpoint a couple of pain spots specifically in a classification setting. And after that, I think we should be able to jump right into convolutional network. So this way, I kind of set the tone up so that, after the foundation, you can just fly from there. All right, I think somebody else had a question, asked me if the forward propagation and backpropagation only applies to regression. No, it applies to both regression and classification problem. Any neural network-based model can accept forward and backward propagation. So yeah, that's a good question. Sam, you got it? Okay. All right, so yeah, that's a good question, and the answer is no, right? Not just regression, but also for both, right? Regression and also classification. And as a matter of fact, any neural network-based model, they all have this structure: forward, backward, they all have it. Okay. All right. Okay, so let's talk about code. Now, first things first is you load up library. You check the TensorFlow library. These are some basic library that you load. We're gonna use this API to load up the data. Okay. So I believe this kind of setup you guys probably already seen it like 3-4 times. So let me know if it's still confusing. There isn't really much to say other than you use API to load up the data, and in this case, there's training data as well as the testing data. And you can do a quick sanity check of the dimension, and you point it out. It's going to be 60,000 by 28 by 28. This 60,000 means 60,000 pictures, okay? And this 28 by 28 means each image is sized 28 by 28. Okay, so the first pain spot I'm going to check with you guys, and this has nothing to do with neural networks, okay, is one of the built-in functionality that I recommend people do in a production pipeline. So what's going on here? This function is called a pickle. Okay, a pickle file. Now, of course, you have to import it, right? Because the library. So a pickle file or a pickle library is essentially acting as a zip folder, but instead of calling .zip, you call it .pkl. So it's exactly nicknamed here pkl. That means pickle. A pickle file is kind of like a zip folder. It stores whatever data that you want. It can be array, it can be tuple, list, dictionary, two-dimensional array, data frame, pictures, so on and so forth. Okay, you can store whatever you want. The reason I suggest this way is because when people do large-scale data processing using a single CPU, they run on memory. And it's very likely that you run on memory, and you're going to probably do that a couple of times, not just on Colab, but also on your own computer as well, if you work on large enough of data sets. And every year is like at least one group of kids that, somehow write some code that, the Python doesn't run. And then they're struggling in their head. They're like, okay, what am I doing wrong? Like, what do I change? Well, no, you didn't do anything wrong. You just wrong memory. Okay, so this way it helps you kind of take care of that problem, and hopefully it will make your life easier, right? So that's the idea. That's the motivation. So now let's take a look at what is code. Why is code going to be helpful for you? Okay, so let's say you have a bunch of data, right? This data is not that big, but let's pretend that this data is huge, okay? And every time you're going to have to download this, it's going to chew up a lot of memory. Let's say, hypothetically speaking, that's the premise. If that's the case, to prevent all of this from happening, all you gotta do is you do a pickle.dump. This way, it will save everything down to this pickle file, and I'm gonna show you how that works. Let's say I'm in my directory, right? Let's say this is my directory. I already run it here because I was running this code earlier. So I'm gonna erase that just to show you guys live what that means. So I'm gonna say delete file. Yes, I want to delete this. Right, so that pickle file is gone, right? So if I do a quick sanity check, let's say I do, I have the code here. So list dirt, it will give me model, this .h5, and the sample data. That's exactly what's happening here, right? So I know that this is the directory that I'm in right now, and let's pretend that's where I want. If you want a different directory, of course, you go to that directory, right? But let's pretend this is what I want. So now I'm going to run this, enter, and then this line is going to put every image, every label in this object called A, and then this with function, you're probably never going to use this again. You're going to say with something open as handle, and then you do a pickle.dump inside of this with statement. Okay, right now just kind of take it for granted that's how things work. You can just copy this entire code and run it by in the Python directly. So the only thing you change is this minus data.pickle, PKL. .pickle, you can't change it, but this minus data, you're gonna have to change it, change the name basically to whatever you want. And once I run this code, which I just did, now it's gonna show up here as mNISData.pkl. And then you do lister again, it's gonna be here, right? PKL. So why is this useful? This is useful because now everything above, data processing, 20 photos that I wrote, right? Whatever complicated stuff that you have, everything above, it's now saved in this pickle file. And then if you run out of memory and it shuts down, no problem. I can just load back up by doing pickle.load. Okay? So right now, let's say this B is, I'm going to override this B as 1 so that this B doesn't have anything in it. It's just number 1. Oops. It's just number 1 and nothing's in it, right? Now I'm going to override this B with pickle load. Pickle load, what that means is it's going to go into this PKL object, load that up, extract whatever's in the middle out, and define as this object B. So the minute I run this code, this 1 is going to disappear. It's going to get overwritten by whatever the new file that I'm loading up. Okay, so double check B equals 1, right? So I'm not cheating, right? B is 1. There's no data in it. Now I'm going to run this. Okay, now you can check out what B is. If I print out B, it's going to be some weird thing, right? All the data, all the arrays, they're all here. Okay, so how do I recognize what this is? Well, you need to know what A is, right? Because that's where you save all of the data in the pickle.dump function. So if you have a 1 parenthesis, that means it's a tuple. And inside of this first tuple, you have 2 things. One is training image, the other one is training label. And that's not end yet. You have a second tuple, right? And there's another 2 things in there. Test image, test label. henceforth, whatever this B is, it has to be exactly these four things. Okay, so these four things now is gonna get inside this B. So if you do a type of B, it's gonna be tuple. Why is tuple? Because you have two parentheses, right? That's one, and then that's two. Two parentheses. Each parenthesis is a tuple. Okay. Now what you also have is the length. The length is 2. Well, you have two things, of course, length is 2. Right? And then all you gotta do is you can extract it by bracket 0. The first bracket 0 will grab this parenthesis. So the format is this: b equals to, this is technically speaking 0, this is 1. So whatever this is, that's b bracket 0. Whatever this is, that's b bracket 1. Okay, so that's what's happening here. And when you extract it, you do the shape, it's going to recover all the dimensions here, which is exactly what you have up here, right? It should be the exact same dimension: 60,000, 28, 28, 60,000, right? And it's the same here: 60,000, 28, 28, 60,000. So then you're good to go. Okay, so then these two things I can get rid of that because then they're gone. Now it makes my life easier, right? Because think about it, if you're not downloading this directly, right? Here we have API, we download it, good. But if you're not doing this, you're doing your data processing, you clean up all the streams, and you're turning whatever data in a nice matrix form, and you're also doing making sure that there's no NA values, everything's numbers, right? You do a bunch of stuff. You don't want to lose all that work simply because your computer run out of memory. Does that make sense? This way, it saves everything locally, and you will never lose it. Okay. Of course, you gotta make sure that this is in your own drive, right? If you do on a virtual machine, and the next time you change your kernel or you open up it again tomorrow, you're gonna lose all of these files. So make sure that you save it locally or save it on your own Google Drive. Right. So that's the first thing I want to say. Next, after that, you plot a picture, you check the labels, all that stuff we've seen before. We talked about one-hot encode before. And then this is a categorical function, which is essentially just a one-hot encode. I actually missed this part on Thursday lecture. I was going to the YouTube video, I was kind of feeling embarrassed, but that's essentially what happens, right? Sometimes you miss it, and if you miss it, then your performance is not going to be that good. So make sure you have one hot encode if you're a classification problem. And after that, you're essentially all set. You can probably rescale it. You don't have to rescale, but rescale just make sure everything is between 0 and 1. So you have like a smaller range to work with. And that's probably about it. And then, activation function, we talked about all of that, so I'm going to skip that part. Softmax, we talked about that. I'm going to skip that part. Now, let's talk about this. This is the only thing we have not talked about. It's called a regularization. Regularization is actually a little bit tricky to explain because it builds up on the understanding of the optimization problem. Okay, so here's what's happening. If you have these reg contours you define as loss function, it's like a high dimension loss function that you're looking at from the air, like you're looking down. So you can draw them kind of like contour. And this black dot in the middle that says W hat, that's like the best spot, right? It's like the lowest spot because that's kind of like how contour lines work. And then once you have that, you can kind of say, well, if that's the best spot, then the idea is I'm gonna want to get it, right? I do my gradient descent, I zigzag, and eventually I get it. But here's the problem. Whenever you're in a regularization problem, regularization is essentially designed to avoid overfitting problem. So here in this demonstration, we use W1 and W2. Probably won't be able to run into overfitting, but in terms of small demonstration, that's we use 2 dimension as an example. W1, W2, that just means you have 2 parameters. Okay, and overfitting means, hey, maybe one parameter is kind of like a redundant, and it's like overkill. You don't need 2, you can maybe just need 1. Okay, let's say that's the case. If that's the case, regularization problem or regularization will help you take care of this problem. Okay, so how does that work? Where's my pen? Okay, here's my pen. Let's say you have W2 and W1. So what are your choices? W1, W2. You can say, I don't like either of them, right? That's a choice. No, no. Or you say, hey, I like the first one, I don't like the second one. So yes, no, right? Or the reverse. I don't like the first one, but I like the second one. So no, yes. Or the last one, I want both of them, right? I want all the parameters in my model, right? So yes, yes. So basically this means you have 4 choices. 1, 2, 3, 4. 4 choices, okay? Which one is the best one? Well, regularization problem will help you answer that, right? So exactly how will you do it? Well, to work out this model, you need to have some sort of constraint. You need to tell your computer, you say, this is your loss function, but that's not good enough. This loss function needs to be subject to a certain constraint. Meaning what? Meaning I'm either giving it a square one or I'm going to give it a circle one. The square one, it's an L1 regularization, and the circle one is L2. And I'll write out a formula for you. L1, the constraint is W1 plus W2 needs to be less or equal to some certain threshold T. Okay, so that's the L1. L2 is W1 squared plus W2 squared need to subject to certain constraint. And since this is W1, W2, you draw it out, it kind of looks like a square. But if it's W1 squared and W2 squared, it kind of looks like a circle. So what this means is W1 and W2 must be inside of this diamond-shaped area. And what the second formula is saying is W1 and W2 must be inside of this circular-shaped area. So in other words, you can't take this dot, you can't take this dot, you can't take this dot. None of those options are available for you. You're only subject to this small area, either a diamond or a circle. And then you work out your gradient descent, and you're going to realize that for L1, the first type of regularization on the left-hand side, you're more likely to hit these corners. You're not likely to hit the edge. You're more likely to hit the corners. Okay? If you hit the corners, what can happen? Look at this corner. This corner, what's interesting about this corner? This corner, the x-axis or the W1 axis is always 0. So it's always 0, W2. And then same with this corner. What's interesting about this corner? On this corner, all of the W2s are all 0. Right? You have a W1, 0. So what does that mean? If you are in L1 regularization, it will lead you to these 2 choices more likely. That's the difference. Okay? So you're more likely to say, oh yeah, I'm either taking 1, not 2, or I'm taking 2, not 1. And that's it. But if you are in L2 regularizer, you're going to more likely be in this choice. Because then it's more likely that you're in this spot, or in this spot, or in this spot. It's unlikely that you're here, and it's unlikely that you're here. And if you're in this spot, guess what? What is the sign? This is a plus and plus. Because you're in that region that W1 is positive, and W2 is also positive. If they're positive, then that means what? That means you're using their numbers, right? If they're 0, you're not using their numbers, right? This is basically 0. This is basically 0. So that's the difference, okay? So that's kind of how things work. Usually, no one considers that scenario because if you have a scenario that you're not using W1 and you're not using W2, then technically you don't really have a model, okay? So this means you don't have a model. So there's no modeling. So typically people kind of ignore that because if you don't even want to do the modeling, then you're not even using this model. Then it's a completely different conversation. Yeah. If you're doing the modeling, if you want to use the model, and then you have 2 parameters. Okay, let's talk about different scenarios. Right. That's kind of how the story goes. So with that being said, that's a regularization. It's not hard. It's just a different set of thinking. And if this still confuses you, let me know. Somebody had a question, what is WB and RB? That's a good question. So WB and RB in the pickle file, or whatever the pickle function is, this WB means write byte. I'll type it for you. It's write byte, and this RB means read byte. It basically means you're breaking the file down in a byte size or bit size. I don't know what's a I'll just say byte size, and then you either writing it or you're reading it. Writing it means you're saving a file, so you're generating a file. Reading it means you're loading something up. Okay, so that's the difference. Yeah, that's a good question. All right. So with that being said, now I think we pretty much have all of the building blocks. That's regularization, and then let's just fly through this. I mean, there isn't really a whole lot to be said. This is just me playing around, so let's skip that. Really, that's the model. That's really it. You use your sequential API, and then you flatten the layer. That's why you have a flattened layer. Means what? Means you take each pixel and you flatten into one big vector, right? And then you connect it with a couple of dense layers in the middle, and at the end of the day, you're making a prediction. So hopefully this is clear, right? You have x coming in, and you have flattening means this, and then you're going through 3 layers, right? 1, 2, 3. So this is 1024, and then you have second one, that's 512, and then you have third one, that's 64, and then you have 10 of them. This is 1, this is 10, because you have 10 classes, right? And then now all of these should be very clear for you. ReLU, 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 and then softmax. Okay. We haven't talked about bias, but that's actually easy to interpret. Let's write out. Let's say you have x1 here, you have x2 here, and then you're going inside, and you have an A, right? Bias means you have another neuron here that is a constant number, and you do this. So this B is exactly same as the intercept term of your regression model. So you have a y equals to beta 0 plus beta 1 x1 plus beta 2 x2. x1 is here, right? x2 is here. The weights is here. That's beta 1, beta 2. And this is exactly your intercept term. So if you say bias is true, that means you want to use this B term here. If you say it's false, then you're forcing this to be 0. So that's the difference. It just means that your layer has one more neuron that you have to train. That's all. Okay, so with that being said, I think that's pretty much about it. The rest is easy. You just do your fitting, and you do a compile, and then you do your mod fit. So here I actually have a GPU set up. Well, if you want to use GPU, here's another trick. You go to runtime, you say change runtime, and then this hardware accelerator, there's a drop-down button. You click on that, you click on GPU. The default, I believe, is none. None means you don't have any, right? So if you don't have any hardware accelerator, that just means that you're using CPU. Okay, so people ask me, is this necessarily faster? Well, the answer is yes, if you hold all the other factors the same, it is faster. But of course, it depends on how you code your algorithm and how big your data is, and if your algorithm is efficient, and so on and so forth. Based on my experience, I think GPU probably has less memory. So if your memory is your first priority, now of course use CPU. But memory, if it's not the first priority and you just care about speed, then kind of drop the data set a little bit, right? You just work on the speed, so then you throw everything on GPU. Typically, I think there's a trade-off between speed and how much memory you have. Although I don't really know if there's any strict science behind it. Like I'm not a computer engineer, so I can't really explain all that theory for you. But I think intrinsically there's a trade-off. Basically, it means that there's no computer that can have a lot of memory and also super fast. It's very difficult to have that. It's very difficult to have one computer solve both problems. Usually, it's one way or the other. There's like some sort of intrinsic trade-off. I've heard a presentation earlier like 2 weeks ago online that somebody is doing something about quantum computing, and it turned out that the solution to quantum computing is to balance out this trade-off. And one way that people tackle this problem is to use this weird material that's made of whatever, like titanium or something, that can somehow it's like super heat resistant. So it's able to run the computation with very low temperature, and somehow that solves the problem. So then I was like, okay, you're telling me the next 50 years of human evolution is to switch a metal in the computer chip? And turn out that's the case. It turned out that's what people are trying to do. They're trying to switch the metal component in the computer chip, so that hopefully, you know, as your computer is running the computation, like the temperature doesn't blow up, right? Right now, if you're just buying your regular computer from Best Buy or whatever, or desktop, right? They have like a fan inside of your laptop or desktop, which, as you can imagine, like we're talking about a fan, so how low the temperature can that be? Right? So that's crazy. It turned out the solution is really from like a material point of view. You solve a problem. Basically, you come up with a new material that the temperature doesn't blow up. That's kind of what's going on here. So I thought that's a small story for you guys to know what's going on really when you're trying to change in between things. It's not always the case GPU is better, okay? Yes, I know it's fast, but it's not always the case it's better. So yeah, I think there's definitely a shot in quantum computing. That's like another question that people ask, right? Like, next step, next stage of human evolution, like what does AI look like? Quantum computing is definitely one of them. I don't know what that will look like. I don't know how fast that can get. All of us have 5G cell phone right now, and people claim 5G is like the next thing. And like, my computer, my cell phone is like, it took me like 5 minutes to connect to internet yesterday. So I don't know. But yeah, we're I think overall, people are still trying to do their best in each field, but it just takes time. So kind of be patient with this. This is the same story here. I went on a big tangent just to tell you guys the same story here. As always, there's a trade-off, right? It's up to you to design your own data science project so that you have different priority, right? When you process the data, maybe you worry about the memory just a little bit, right? Because you need to save all the data. Okay, so then maybe that's top priority. Then maybe you work on CPU. Okay. But then after that's done, you save everything down to pickle file. Good. If you lose it, fine, no big deal, right? Memory is not a top priority, but the speed is top priority because this thing is due in 5 days. Okay, you gotta do a presentation on Friday. Okay, then in that case, when that day comes, right, tomorrow, Wednesday, whatever, right, then let's drop the priority for memory. Let's shoot for the priority for speed. That speed is your priority, right? Then you work on GPU. Okay, so that's the strategy here. So you gotta come up with a plan that kind of change the software, hardware, the software and the hardware, so that you can work absolutely the fastest. Like it's there's an optimal point there that you have to figure out. Okay, so hopefully today's course kind of set you up to have that understanding, and then when you work on your project, then you're gonna know exactly what I'm talking about. You're gonna be like, okay, let's load this up. This doesn't work. I run that too many times. Let's put a pin in there. Okay, let's continue, and so on and so forth. So you're gonna work that out with your friends, with your teammates, and eventually you're gonna realize, okay, people have different priorities. There's a beginning, there's an end, and we gotta respect each priority. Okay. So hopefully that kind of paints like a relatively clear picture. But if that's still unclear, let me know. All right, so you have the model, you fit it, you basically train a model, and I think pretty much after that it's straightforward. The last thing I want to give you guys is this .h5 file. This .h5 file, I should probably have a link explain this. Let's just Google it. .h5 file. I think the Google is probably a better explanation than mine. Yeah, so there it is. So .h5 file, the h5 is kind of coming from the word HDF. It means hierarchical data format. Really what it means is it's a standard format to save multi-dimensional arrays. Okay, and that's exactly what neural network is. All neural network come down to be arrays. It's just higher dimension. That's all. You can kind of convert what we're doing to exactly arrays. Like this stuff is kind of like an array. And let me show you the model. Where's the model? Like this stuff is actually an array. Like think about 1024, right? You have 1024, but then notice that it's like fully connected, right? So what's fully connected? It's like the graph I draw earlier, right? You still have a x1, x2, x3, and then you have a1 and a2. So you gotta work out each line, right? That's one, that's one, right? So you gotta work out each line. So each line, you can kind of think of that as like an array of numbers, right? Let me use these three, purple. Maybe there's like a number here, number here, number here, right? And then you do another one. Let's say blue line, it's another model, and then that's another array, right? So how do I know what this model is? Well, in computer, I just save these 6 numbers, right? I just save this number, and I save this number, then I'm done. Then I can do my usual computation. I have a model, okay? So what is this? This is exactly an array, right? You just add a bracket, that's an array. And if that's an array, guess what? It can be saved as a .h5 file, all right? So that's what's happening. So the reason I'm explaining that is because here, whenever you save as .h5 file, it will of course depend on where you save it. Right here, right now, I'm in this directory that technically speaking is actually a little bit dangerous, right? Because it's on my virtual machine. And tomorrow, if I lose a kernel or I lose a memory, guess what? I'm gonna lose everything in here. So my recommendation is you mount your drive. Here, let's try it. Mount your drive, and it's gonna say run this code, right? It'll say yes, run this code. And then I'm gonna say connect to my Google Drive. And it's gonna ask my credential, and I say yes, and I say allow, and then it's gonna mount it. And after it's done, it's gonna create a folder here called drive. It's right here. So I click on it, and I click on my drive. Now this is all my stuff, right? And then I can just grab one of these files that I saved. Let's say it's this file, which is saved here. I just grab, I can toss in there. Make sense? I can just toss in there. And once I toss in there, I will never lose this, right? So I'm not gonna do that because this is just sample test. So I'll just leave it here. But for you guys, please make sure don't lose your model. Okay. As a matter of fact, I'm gonna impose this as a requirement. So for those of you who end up choosing TensorFlow as your model, you're gonna have to save this and then save on your GitHub in the very end. And GitHub is actually one of the submissions. I'm gonna write up a small recap for today. So hopefully, this will reinforce the understanding of what does it mean when you work in production. Okay, you gotta save a model, you gotta put the model somewhere so that somebody else can use the model, right? So that's kind of making the connection of how does it work in school and how does it work in real world, all right? And for those of you who somehow, I think a couple of you missed maybe a part of the lecture on Friday, last week. Friday we talked about how to write an installable GitHub package, and along the way, you somewhere down the road for this week, doesn't have to be today, but somewhere down the road, you're gonna have to create that package yourself, and every team has to create that package because that's one of the submission for the project. And then I'm gonna be checking this part, so please make sure that you have this .h file saved and upload to the GitHub. All right, so I think that's pretty much all I want to say about artificial neural networks. Any questions? Good. All right, awesome. So with that being said, we have a few more minutes. One last thing I want to give you guys is I believe we can jump ahead to talk about CNN. All right. So I'm not going to go to the code because I want to talk about theory first. So I'm going to talk about a couple of things. let's see. Yeah, I'm going to talk about this. I'm going to set this up as a theory, and then we'll use tonight kind of like a buffering, because today is a lot of context, and tonight we're going to use it as a buffering to help you guys just slow things down just a little bit, because today is a lot of materials. But I do believe most people are ready for this. So one of the special type of convolutional neural network that it's going to extend to like autoencoder or image segmentation or other image-to-image model is called a convolutional neural network. The convolutional neural network 20, 30 years ago is kind of like a new discovery, but right now it's kind of like a basic building block that you always have to know. And no one really talks about this, but the first thing about convolutional operation is that it's the data are all images. Okay, so if you have a tabular data or some sort of CSV spreadsheet, then usually the recommendation is to try to avoid convolutional neural network, unless you can somehow put the columns together in a weird order that they somehow make sense together when they're next to each other. Other than that, it probably won't make a whole lot of sense if you're working out the convolutional network and then you're like on tabular data, right, on a CSV file. So the key point here about convolutional neural network or CNN is that the underlying data set is image. Okay, so the image data has this one important property called the invariance property. The invariance property, well, kind of like as the name suggests, right, invariance, right, doesn't change. So what does it mean it doesn't change? So think about this. This picture is a bear and it's reading a book, seems like it's sitting here, right? I know that this is a bear, and I know that I know, and if you rotate this, it's still a bear, right? And as a matter of fact, you can even like make a cut in the middle and separate the head and the body, and you show me the picture of the top side of the picture, I can still recognize that it's a bear, even though it's just the head, right? Let me show you. So you can take this, you can rotate, and then it's gonna look like this. This is the head, this is the ear, right? And this is the body, this is the arm, right? And there's a book here, right? I'm still going to recognize that this is a bear, okay? Or you cut a line in the middle, right? And this top part, you take it out and you block this out for me. You block it out, right? You throw away, take the top part, throw away. And then you just show me the top half. And you're like, okay, what is this? Well, it's a bear. The recognition doesn't change, right? The decision doesn't change. It's still a bear. The decision doesn't change simply because you've done something to the picture. So that is called an invariance property. Okay, it's as simple as that. So what does it mean, right? What does it mean? It means that if you somehow, if you give me a x1, x2, x3, x4, this x1, x2, x3, x4 together form a 2x2 small cluster of image area, image location, right? Just 4 pixels. You put them together, right? These 4 pixels, if it's the ear, right? If it's the ear, then it's always the ear. It doesn't matter where it is. So in other words, the information of that ear is somehow preserved in the combination of these 4 pixels, yet it doesn't lose the information even if this information is removed and goes somewhere else in the picture. Let's say this is a bigger picture, right? And this is maybe 3 is here, 4 is here, maybe this is 4x4, like this. What if I take this information here and then I put it here? Let's say x1, x2, x3, x4. I'm still going to recognize that this is the ear, right? So in other words, the information is somehow able to preserve, disregard the location of the picture. Okay, so in other words, I can somehow shuffle the column of the data and somehow your prediction is the same. Okay, so that's what we call an invariance problem. So how do we take care of that problem? We use a thing called a convolution operation. Okay, so we're gonna talk about that, and hopefully I can finish this in like next few minutes. It's really not that hard. So a convolution layer is essentially a layer of kernels or filters that we apply convolution operation to. Okay, so a kernel is exactly a small matrix just like that, and an image can be thought of it as this matrix above. And the convolution operation is defined as you take this kernel and then you apply it to the first row and first column. Let's say this is R1, row 1, and this is column 1, C1. So we're going to start from here. And once you've done this, you're going to rotate to the second column, and then third column, and then fourth column. And once you're done with the first row, you're going to come down to the second row, and then first column, second column, third column. And then third row, and then first column, second column, and third column, and so on and so forth, right? You have this rolling window motion. Okay, so that's the idea. Now, where's the math? The math is actually very simple. The math is called the element-wise matrix multiplication. Okay, it's actually super simple. All you gotta do is you take this matrix that's 2 by 2, that the numbers are 1, 1, 0, 0, and then you apply on the top left corner here, which is gonna give you, which is essentially gonna overlap with the top left corner, but only up to the second column and the second row. And once you apply this operation and they overlap, you do an element-wise matrix multiplication. So what that means is you take this number 1 and then you multiply this number 1. That's what's written here. And then you take this number 2 and then you multiply this number 1, and that's what's written here. Now, since the next two numbers are all zeros, then there's nothing we can do, right? Because 0 times 5, it's 0. And then 0 times 4, it's also 0. So there's nothing we can do, they're all zeros. So then you're like, okay, what's next? The next is you take these numbers and you add them together. So what do you have? This is 1, right? This is 2. And then these are 0, so that goes away. So 1 plus 2 is what? It's 3. And that's it. That's essentially what a convolution operation is. Okay. So typically, I do this every year, and I tell the story for like half an hour, and when I actually explain the math, it's like 2 minutes. So that remains to be like a common theme in neural networks, which is super fascinating to me, because usually I have to usually I motivate the story and I explain the premise, I explain the assumption, I explain what the data is, I explain what the matrix look like. And once I finish all those things, it's like half an hour. And when I actually explain the math, it's like 2 minutes. Okay. And then now you guys get the idea, right? Now we're gonna move on to the next one. So you take the same matrix. Let's just switch different colors so we know that we're talking about something different. Now, once you're done with the first column and the second column, you move one column to the right, which is what? Your second column and third column, right? So of course the number changes a little bit, but the 2 and 4, that stays the same, right? So now it's a 1, 1, what do you have? You have 2 and you have 6. All right, that's here, check. 0, 0, nothing we can do because this is 0, this is 0, so it doesn't change anything, right? You're just adding zeros. So 2 plus 6, well, that gives you 8. Done. Right, that's another convolution operation. Okay, then you guys get the idea. You just keep going, right? So once you're done with, where's my pen? So you're done with this, check. Then you're done with this, check. That gives you these two numbers, right? And what's next? You go down, right? Because you're done with the first row. You're done with the first row, you can't continue. Then you come down to the second row, right? Second row is here, right? That's the second row. That's the first row. That's the third row. So second row gives you what? 5, 4, 5, 6. So then it's going to give you 5 and 4. That's here and here. Zeros goes away. Then that's 9. And then the last thing is the same thing, right? 4 and 5. So 4 and 5, that gives you 9. Done. Done. All right. So that is essentially your convolution operation. So a convolutional layer is essentially, you tell the computer, you say, okay, this 1100 is a little bit problematic. I don't like that. Why do I have to do 1100? Why can't I do 1200? or 1300 for that matter, right? There's no science here. This 4 numbers is complete arbitrary. So there's no reason I have to stick with 1100. I can, as a matter of fact, change whatever I want. Right? And that's exactly the case. People do change whatever they want, right? There are a list of different filters that you can use. Sometimes you hear people say kernel. Kernel, kernel is kind of like referring to this particular 2x2 area, and a filter is kind of like a special set of kernel that extracts certain information into the neural network. So for the sake of this class, it's okay. You can use them separately. You can use them interchangeably. People understand what you mean. But if you truly dig into like the foundation of the idea, people sometimes disagree. But from my point of view, I think maybe it's a little bit overkill to waste your energy on that. You can say kernel, you can say filter. I think that's fine. So the whole point of this is some people, they put a lot of energy on what this filter is, right? I'll show you. So there's this thing called a Gabor filter. Gabor filter. So Gabor filter is essentially kind of based on Gaussian process, and the power of Gabor filter is it actually all looks like this. So it kind of looks like some sort of a light spectrum that somehow it's all generated by these contour circles. Like you kind of see that like one of these kind of like contour. I don't know if you can see that. And this is also another contour, and this is also another contour, and all they're doing is they're somehow generating these how do you say, like kind of like egg-shaped circles, and then they're rotating it like clockwise, and then each time you rotate, it extracts certain information from the picture. And I don't know if you have a good example. Here's a good example. This is what a Gabor filter looks like when you're applying on the original picture. So you have a person's face, right? Eyebrow, eyes, nose, mouth, right? And if you do Gabor filter, it's somehow able to preserve the original shape, but only the horizontal information. The original picture, there's many more to just horizontal one, right? There's eyebrow, there's eyes is a circle, right? Nose, you have this shape, and mouth, you have this shape, right? A human face is like a lot more shapes than just horizontal, right? But if you look at only what's coming out of this filter, which this filter by itself is horizontal, right? This is horizontal. Then the information that's somehow coming out of this filter, the filter response, is actually this thing. So which is super fascinating, because anybody see this picture on the third picture here, you can somehow still kind of tell that there's a person's face here somehow. So that's the magic about filter, right? It's losing some information from the original picture, but it somehow captures the essence of other information, right? That's what a filter do. You erase some information and you preserve some information, and somehow you do this many times over the entire neural network architecture. Overall, the performance is good. So that's what's happening. All right. Okay. Awesome. So I think that's probably not a good picture, right? If you have a diagonal filter, then of course you can only extract the diagonal pattern on the zebra, right? And everything else is blurred out. Okay. So if your goal is to identify the diagonal pattern, you use a diagonal filter, right? And there are like a million filters. I mean, there's like so many different filters out there that you can pick. All right, so it's about 8 o'clock. I'm gonna stay here a few more minutes in case there are questions. But if not, then you're good to go. And please make sure to get your project started, get your team started, set up that Slack channel, and please ask Sam and I. And then after that, I think yeah, I'll just send you guys the Slack message. And then with that being said, I'll see you guys tomorrow.
I'm gonna be absent tomorrow.
Oh yeah, got it. No problem. So Sam will take notes of that, and we'll take care. Yeah, thank you.
Have a good one.
Yeah, have a good one. Bye, Sam.
Hi, I had a few